Lecture 4-2, Covalent Bonding and Molecules. First, the definition. A covalent bond is a chemical bond in which two or more electrons are shared by two atoms. So why should two atoms share electrons? Well, basically, we're going to think about it to start out with in order to fill their valence shells. Down below is the Lewis structure. We will get to Lewis structures later of fluorine. Fluorine has 7 electrons around it, and you pair it up with another fluorine, and they can share a pair of electrons, and each of the fluorines appears as if it then has 8 electrons around it, with 2 being bonding electrons here in the middle, and the other 6 being lone pairs on the outside. So this here forms the covalent bond, and these other 6 form 3 lone pairs. A molecule is an aggregate of 2 or more atoms in a definite arrangement held together by chemical bonds. They can be the same atoms, as in hydrogen molecule, or they can have different atoms, as in water or ammonia or CH4, which is methane. We can classify them as diatomic, that is, they have only 2 atoms. They can be homonuclear diatomics, like hydrogen and nitrogen, oxygen and bromine, having the same atoms bonded together, or they can be heteronuclear, like hydrogen chloride or carbon monoxide. Polyatomic molecules have more than 2 atoms. Ozone, water, ammonia, and methane are examples down here at the bottom. Chemical formulas. A molecular formula shows the exact number of atoms of each element in a molecule in the smallest unit of that substance. For example, water is H2O. And we know that each water molecule has 2 hydrogens and 1 oxygen. Into H4 down here is 2 atoms of nitrogen, 4 atoms of hydrogen to make an individual unit of that substance. An empirical formula shows the simplest whole number ratio of the atoms in the substance. Basically, if you can divide each of the subscripts by a number, you will end up with an empirical formula. In some cases, however, the molecular formula and the empirical formula are the same. So, for example, here, water, H2O, can't be reduced any further. Therefore, its molecular and empirical formulas are the same. The next one is C6H12O6, which is a generic hexose. Most people would think of glucose, and each of these can be divided by 6 to give CH2O. And as a side note, this is where we get the term carbohydrates from. Carbohydrates have the same empirical formula, carbon followed by a water in the empirical formula, so carbohydrate. The next one is ozone. Ozone is O3. We can simplify that down to just simply O. And the bottom one, hydrazine, can be reduced from N2H4 to NH2. Allotropes are distinct forms of an element. They each have different chemical formulas and chemical properties. They are distinctly different from isotopes. Isotopes have different numbers of neutrons in the nucleus. Allotropes have different numbers of the individual element in them. For example, here, oxygen, which is on the left, is O2, and ozone, which is on the right, is O3. They have separate and distinct properties. A structural formula shows the distinct arrangement of atoms in a molecule. Below are 4 different types of structural models of, in this case, ethanol. The top left-hand picture is simply a line drawing. It shows how each atom is connected to each other using the atomic symbols for the carbons, hydrogens, and oxygen. Next to it, in the top right-hand corner, is a ball and stick model. In essence, each atom is represented by a ball, and it is connected to other atoms by a stick. In the bottom left-hand corner, what we have here is a condensed line structure. This is one of the ways organic chemists will quickly draw a structure, because we can leave out the carbons and hydrogens and understand what it means. And finally, at the very bottom right is a space filling model, which kind of looks like a ball and stick model with everything being fat and there are no sticks. Basically, it's a representation of how much space each of the atoms will occupy when you make the molecule. Now we're off to naming these molecular compounds. Looking at naming of molecular compounds, to let you know, molecular compounds are nonmetals bonded with nonmetals or nonmetals bonded with metalloids. Metals are not involved in most molecular compounds. Some compounds have common names. For example, H2O over here is just simply water. NH3 is ammonia. CH4 is methane. And this thing, C sub 60, which is one of the allotropes of carbon, is called a buckyball. In naming molecular compounds, the element that's further left in the periodic table generally goes first, or the element that's closest to the bottom of a group goes first. And seeing how we will be dealing with binary compounds, there will generally not be a lot of confusion about which one is further left or which one is closest to the bottom. If you can form more than one compound from the same 2 elements, we're going to use the prefixes that are listed here in this table, these Greek prefixes, to designate the number of each kind of atom. And then finally, we're going to treat the last element as if it were an anion and change its name to its IDE form. The Greek prefixes are used again to designate how many we have. However, we will not use mono at the beginning of a name, and anytime that we encounter oxygen, we end up losing O's and A's before we put it with oxygen to make an oxide. More on that later. So just to reiterate, the prefix mono is not used at the beginning of the name of a binary molecular compound. For example, PCl5 is phosphorus pentachloride, not monophosphorus pentachloride. And again, if the prefix ends in an O, as in mono, or an A, like penta, tetra, we are going to drop that vowel before oxide so that we don't have two vowels right next to each other. For example, here N2O5 is dinitrogen. We have Di before the nitrogen to designate that there are two nitrogens. And then pentoxide, not pentaoxide. So here are some examples. HI is hydrogen iodide. There's no monos in hydrogen and iodide because there's only one way to put hydrogen and iodine together. Hydrogen and any of the halogens, iodine, chlorine, bromine, fluorine, only form one compound, and therefore we will not see mono in any of the hydrogen halides. NF3 is simply nitrogen trifluoride. Remember, no mono at the front there. SO2 is sulfur dioxide. Next is N2CO4, so di for the 2, dinitrogen, tetra for the 4, tetrachloride. Next is nitrogen dioxide. Looks just like sulfur dioxide, except we have a nitrogen in it. Just as a side note, don't breathe this. It is toxic. And then the next one, N2O, is another way of putting nitrogens and oxygens together. So we have dinitrogen. Again, the 2 is designated, but now we need the mono prefix for the oxygen, monoxide. So dinitrogen monoxide, also called nitrous, it is laughing gas. You can breathe that. Many of the hydrogen compounds, when mixed with water, will make acids. And when they're dissolved in water, they release a hydrogen, which is the reason they become acids. In their non-aqueous state, that is typically as a gas, sometimes as a liquid, we will name them using our binary molecular nomenclature. So HF, for example, when it has a G next to it, gas, is hydrogen fluoride. But once we put it in water, aqueous, with an AQ next to it, now we're going to change the name. We're going to lose hydrogen and put in the prefix hydro. We're going to change the fluoride to an ic acid. So we're going to leave the root name in there, and now we have hydrofluoric acid. All of these are binary in nature except for one, and that is HCN. It is a polyatomic, but it's put in here because CN minus has the name of cyanide. And it is like fluoride, chloride, bromide, iodide, ends in IDE. So we're going to change that to hydro for the hydrogen, and then ic acid, just as we would any other IDE compound above, and this becomes hydrocyanic acid. So let's name a few. HF in the gaseous form is hydrogen fluoride. NH3 has a common name. It is ammonia. P2O5, the phosphorus has 2, so it's diphosphorus. And pentoxide. Remember that we lose the A from the penta when we have 5 oxygens. Next is xenon, not monoxenon, xenon tetrafluoride. The next one is bromine triiodide. And then finally, H2S is not hydrogen sulfide because it is aqueous. Remember, we lose the hydrogen and get a hydro. And then sulfuric acid. Again, aqueous, hydroic acid.